Welcome to The Explainer. Today, we're going to talk about a paper from 2014 that, honestly, changed everything. We're talking about Generative Adversarial Networks by Ian Goodfellow and his colleagues. This wasn't just another research paper. It introduced an idea so elegant and so powerful that it basically kickstarted the entire modern generative AI movement we're living in right now.
So here's what we're going to cover. First, we'll set the scene and look at the big problem researchers were up against back in 2014. Then we'll unpack the paper's brilliant solution, this game of fakes. After that, we'll see how you actually train these dueling networks, check out the very first images they ever created, and then wrap up by exploring the incredible, lasting legacy of this one idea.
Okay, so let's rewind to before 2014. If you wanted to get an AI to generate something new and realistic, like a picture of a face that doesn't exist or a handwritten number it's never seen before, it was just incredibly difficult. The whole process was a computational nightmare, and the results, well, let's just say they weren't always that convincing.
I mean, really, think about it. How do you teach a machine to dream? That was the big question, and researchers were kind of stuck. The models they had at the time, things called Boltzmann machines, were notoriously slow and just way too complex. They had to rely on these clunky approximation methods and these things called Markov chains that, really struggled to produce sharp, believable results. The field was desperate for a breakthrough.
And this table really just lays it all out. You can see the huge bottleneck everyone was facing. The old methods were tangled up in this super complex, sometimes even impossible math. It was slow, it was inefficient, but this new adversarial approach, it promised a much cleaner, more direct path using standard tools that everyone was already familiar with, like backpropagation. It was a total game changer.
All right, so let's get to the breakthrough idea itself. Instead of trying to build one single, massive, complicated model to do everything, the authors proposed something, well, kind of radical. Why not pit two simpler networks against each other in a kind of high-stakes competition?
And I love this quote from the paper because it just perfectly explains the whole idea. It's so intuitive. You've got a forger who's trying to make perfect fakes and a detective who's trying to spot them. It's the competition itself that forces both sides to get ridiculously good at what they do.
So, let's meet our two players. On one side, you've got the generator. Think of it as our counterfeiter. It takes a bunch of random noise and tries to turn it into a convincing fake image. Its opponent is the discriminator. That's our police detective. Its job is to look at an image and decide, is this real from the original training data, or is it a fake from the generator? They are locked in this perfect adversarial tug of war.
So, how does this game actually make them smarter? Well, the training process is this really elegant feedback loop. Every time one of them fails, it becomes a crucial lesson for the other one to get better.
Now, don't let the math scare you. This is the mathematical heart of the paper, but you really don't need to parse the whole formula. Just get the big idea. It sets up what's called a mini-max game. All it means is the discriminator, D, is trying its best to make this value as high as possible by correctly spotting fakes. And the generator, G, is trying to do the exact opposite. It wants to make the value as low as possible by creating fakes that are so good the discriminator gets it wrong. It's a zero-sum game, where one's win is the other's loss.
And this simple three-step loop, just repeated thousands and thousands of times, is the engine that drives the whole thing. The discriminator sees a mix of real and fake images. It makes a guess. And then, this is the critical part, the feedback from its performance goes right back to the generator. If the discriminator spots a fake, the generator learns exactly what it did wrong and tries something new. Through this constant battle, the generator's fakes get better and better until they're basically indistinguishable from the real thing.
Okay, so that's the theory. It sounds great, right? But did it actually work? This is the fun part. Let's take a look at the very first images ever cooked up by a generative adversarial network.
So these were the first results, trained on that famous MNIST dataset of handwritten numbers. Now, they might look a little basic to us today, but believe me, in 2014, this was a huge deal. And check out that column on the far right. The authors cleverly included it to show the closest real digit from the training set. Why? To prove that the network wasn't just cheating and memorizing. It was genuinely creating new digits from scratch. And the model showed it could be versatile too. On the left, yeah, you see those sharp digits. But on the right, you can see its first shot at the much harder CFR10 dataset, which has pictures of real-world objects. The images are pretty blurry for sure, but you can definitely make out the shapes of horses and cars and dogs. This was the first hint that this idea had the potential to generate way more than just numbers.
And here's the other crucial piece of evidence. The network wasn't just spitting out random pixels. You can see here how it can smoothly morph one generated number into another. By doing this, the authors showed that the model had learned an actual underlying concept, a sort of idea space of what makes a 1 and a 5 a 5. It was starting to understand the structure of the data itself.
So all of this brings us to the paper's absolutely incredible influence. I mean, the ideas presented here didn't just stay in a lab somewhere. They exploded across the entire field of AI and really did set the stage for the generative revolution that we're all a part of today.
You know, the authors themselves had some amazing foresight. Right there in the paper's conclusion, they laid out a bunch of ideas for future work. And that first one, conditional GANs, that is the direct ancestor of the text-to-image models like DALL-E and Midjourney that are everywhere today. They were literally sketching out the roadmap for the next decade of AI research.
And its impact? It's just undeniable. You're looking at one of the most cited papers in modern computer science, period. It's foundational, it's required reading for anyone working in generative AI, and its core concepts are still being tinkered with and built upon every single day.
At the end of the day, the GAN framework really did open a Pandora's box. Its applications stretch from creating synthetic data for medical research all the way to generating the hyper-realistic media that's reshaping our digital world. It's a technology that really forces us to ponder that question on the screen. And as we think about that, just a quick reminder, this explainer is for entertainment purposes only.